When modern readers examine ancient Sanskrit texts like the Srimad Bhagavatam, they often encounter what looks like flat earth folklore. To a 21st century eye, these thousands of years old verses seem to describe a primitive, simplistic cosmos. Curious, this chart highlights a specific contradiction found in the text. It states the sun measures 10,000 units, the moon 12,000, and a shadow entity called Rahu measures 13,000. In our physical reality, the sun is 400 times larger than the moon. The Indian civilization of this era invented early trigonometry and the concept of zero. It seems unlikely that they would make such an obvious observational error regarding the relative sizes of the bodies in our sky. The contradiction is a result of modern literalism. We assume these measurements describe the radius of physical rock because that is how we view the solar system. But if we shift our perspective, the numbers begin to align with a different kind of reality. A planet's physical crust is only its visible footprint. These ancient authors were mapping a three-dimensional topology of invisible forces, the gravitational and thermal structures that actually govern orbital motion. To test this, we have to look at the primary unit used for these measurements, the yojana. This flowchart establishes the conversion rate. 1 yojana equals 12.87 kilometers. Using this math, the text's baseline measurement of 10,000 yojanas translates to 128,700 kilometers. Applying this specific scale transforms the text. It moves away from mythology and becomes a quantifiable framework for the mechanics of the solar system. The text measures the sun at 10,000 yojanas, or about 128,700 kilometers. While the sun's total radius is 696,000 kilometers, its core, the actual engine where fusion occurs, is roughly 139,000 kilometers wide. The ancient measurement describes the internal power source rather than the outer shell. For the moon, the text specifies 12,000 yojanas, which translates to 154,440 kilometers. This matches the moon's hill sphere, the gravitational bubble that controls our tides. Modern science places the edge of this influence at approximately 154,000 kilometers. The largest value, 13,000 yojanas, belongs to Rahu. At 167,310 kilometers, this matches the diameter of the L2 Lagrange point's halo orbit. This invisible gravity well, located behind the moon, is large enough to capture dust clouds that create eclipses. When we move past physical mass and look at these spheres of influence, the supposedly inaccurate ancient numbers prove to be astronomically precise. This table shows the technical precision extends to the language itself. The texts use a consistent metaphorical lexicon for complex physics. A chariot represents a fixed orbital path. The horses pulling it represent the invisible gravitational vectors and velocity pulling a body through space. Even the colors of the horses carry data. Mars is linked to ruby-red horses, matching its high iron oxide albedo. Mercury is described with wind-swift horses, reflecting its position as the planet with the highest orbital velocity in the system. Viewing these lines as simple mythology hides a calculated physics glossary. Every metaphor corresponds to a specific celestial property. We can see this in the description of Rahu, the entity responsible for eclipses. The verses describe its chariot as being both pitch black, tamome, and gray, dusar. As this optical diagram shows, that is a precise description of an eclipse shadow. The umbra is the inner cone of deep darkness, while the penumbra is the outer, grayish region of partial shadow. The text states Rahu is pulled by exactly 8 dark horses. This aligns with the n-body problem in orbital mechanics. The stability of the L2 Lagrange point is governed by gravitational pulls from exactly 8 major bodies: the Sun, Earth, Moon, and 5 visible planets. Rahu's symbol is a waving black flag. This 3D wireframe renders that concept into a physical form. The symbol captures the triangular shape of a shadow cone, the ripple of its orbital wobble, and the inherent instability of the Lagrange point itself. Finally, the texts note that Rahu constantly travels backward. As this diagram shows, this is the mathematics of nodal precession, where the points of an eclipse continuously slip backward against the direction of the planets. The convergence of these independent variables, the 8-vector stabilization, the dual-tone shadow, and the retrograde motion, suggests a model of the L2 point that is too detailed to be a coincidence. These ancient texts were never just stories. They functioned as a three-dimensional mathematical simulation of the cosmos, preserved in verse. But this raises a question. If they possessed this data, why hide it? Why express astrophysics through the language of religion and poetry? It solves the problem of information decay. Physical storage, whether it is paper, stone, or digital servers, will always crumble over long periods of time. The most durable way to ensure data survives for thousands of years is to encode it into a cultural format that humans will protect and repeat. By turning physics into sacred song, they ensured the information would be passed down through generations. These ancient astronomers created a durable cultural transmission, an informational bridge sent across history, waiting for a civilization to translate it back into science.